This is podcast 4.6 for AP Chemistry, and we're going to talk about hybridization and the localized electron model. So the first exercise we're going to do is a quick review of drawing Lewis structures in shapes and geometries. So we'd put carbon in the middle if we wanted to draw methane, and we'd start by putting the 4 hydrogens around it. And if we were tallying up electrons, carbon would have 4 and each hydrogen would have 1. So that would be a total of 8 electrons I could use in my picture, and that's what I would have here because I have 2, 4, 6, 8. So this is the Lewis structure for methane, and then it asks, what is the electron domain geometry of a methane molecule? Well, anything that has 4 domains is going to be tetrahedral. And then it says, what are the bond angles? And the bond angles for tetrahedral are 109.5 degrees. So then it asks more about methane. What is the valence electron configuration of a carbon atom? Well, a carbon atom, if we remember back, is 1s2, 2s2, 2p6. And since they're asking just about the valence electron configuration, we would look at only these second energy level electrons. It says, why can't the bonding orbitals for methane be formed by an overlap of atomic orbitals? So why can't we just take these and overlap them in order to make the bonds that we need with the hydrogens? And the reason is, if we did that, what you would see is that we would see 2 different types of carbon-hydrogen bonds. Because remember that a s orbital has one, we represent it with 1 line. A p orbital is represented with 3 lines. So, that would not be 6, that would be 2. So what we would see is that if we're taking all of these orbitals right here and we're just letting them overlap, we have 2 different types. We have S's and we have P's. But instead what we know is that each of those bonds in methane from each carbon to from the carbon to the hydrogens are identical. And if they looked like this, we would not have identical bonds. So what we're going to talk about today is called hybridization. So assume that the carbon atom has 4 equivalent atomic orbitals arranged tetrahedrally. And that's what we already talked about. You'd have your carbon in the middle with your 4 hydrogens off. And we assume that each of those single bonds to each of those hydrogens is exactly identical. Each of those bonds is identical. It says then that the mixing of the native atomic orbitals, and by atomic orbitals we mean the s, the p, the d, and the f, what they do is they mix together and they form special orbitals for bonding. That's the hybridization that we're going to talk about today. So if we're talking about the s and the p's, they can hybridize together and they form their kind of new hybridized orbital that's used for bonding. So sp3 hybridization is the combination of 1 s with 3 p's. So we're going to take the s and we're going to combine it with the 3p orbitals. Whenever a set of equivalent tetrahedral atomic orbitals is required by an atom, the localized electron model assumes that the atom adopts a set of sp3 orbitals. That is to say that the atom becomes sp3 hybridized. So anytime that we need a tetrahedral, we need 4 bonds, it's going to take 1 of the s orbitals and it's going to take 3 of the p orbitals, put them together, and that's how you're going to get your 4 equivalent hybridized orbitals for bonding. The example that they show you here, this picture, shows the 2s and the 2p. These are unhybridized. This is how they would look. The 2s has a lower energy level than the 2p. So what happens though is when they come together and they hybridize, they kind of change. They form somewhere in the middle in terms of energy 4 identical bonds, the sp3. So each of these is an sp3 bond. This is an sp3, this is an sp3, this is an sp3, and this is an sp3 orbital. That's how you get the 4 identical orbitals from these 2 things, which would not be the same if we left them as they are. Here's just a picture showing that same thing. This is the s orbital, and then we have the 3 different p orbitals. When they hybridize, you end up with kind of this mushroom look to each of the sp3 orbitals, and then they come together and you can see how they end up arranged in that tetrahedral shape. And here's a close-up look then of the methane. So we have our carbon atom and the nucleus being the center here. Here are the 4 sp3 orbitals in that tetrahedral shape. And then you have the hydrogen with their 1s. The hydrogen doesn't hybridize, it only has the 1s and that's it. So that kind of just attaches to those sp3s of the carbon. And that's how you're going to get methane. We can do the same thing with all these other shapes that we've talked about. So it says draw the Lewis structure for oxygen. Well, oxygen's Lewis structure would look like this. That is a lone pair, even though it's very hard to tell. And then it says, what is the shape of an oxygen molecule? Well, an oxygen molecule is linear. That's a linear shape. And it asks, what is the approximate angle between lone pairs of electrons on each of the oxygen atoms? So from here to here, the approximate bond angle would be 120. Because there's 3 domains around each oxygen, they should be about 120 degrees away from each other. And then it says, why can't sp3 hybridization account for the oxygen molecule? Well, the answer would be because we know that sp3 hybrid orbitals have this angle because they're arranged tetrahedrally. That would not suffice for the oxygen because it needs bond angles of 120 degrees. So we're going to have to look at a new hybridization of some orbitals in order to meet that 120 degree bond angle right there. So what we do then is, because we have 3 domains, 3 electron domains, we're going to take 1s and we're going to only take 2 p's. So instead of doing the sp3, which was the 4 electron domains, this time because we only have 3 electron domains, we're going to drop out and leave one of those p's to be unhybridized. So it's the combination of 1s and 2p orbitals. It gives a trigonal planar arrangement of atomic orbitals, and that's what if we were to look at that oxygen, one of those oxygens, around that oxygen is a trigonal planar arrangement because we have 3 domains. And it says that one of those p orbitals is not used, it's left over, and it's oriented perpendicular to the plane of the sp2 orbitals. So the sp2 orbitals, let's say they were all laying flat on the paper, perpendicular would mean it's sticking out at you or going away from you. So it's not in the same plane as those sp2 orbitals. Here's a picture so you can see that. Here's the 1s with the 2 p's. Again, we get that mushroom shape. And when they combine together, you can see how they make the 120 degrees between each of the orbitals. With this one, you have the 2s and the 2p. And instead of all of the p's going together to be hybridized, one of them is left out. So there's your 3 electron domains that are all sp2. We need to talk also about sigma and pi bonds. So a sigma bond is when an electron pair is shared in an area centered on a line running between the 2 atoms. So that just means it's between the 2 atoms. If I had my oxygens, electrons that exist right in the middle here, right between these 2 atoms, those are your sigma bond. Your pi bonds are the ones that form either above and below or in front or in back of the atoms. They are not in between the 2 atoms. They are above it or below it. And this uses the unhybridized p orbitals. So your sigma bonds that we were just looking at back here, they use the hybridized. These use the hybridized orbitals. They're the ones that exist between the atoms. The pi bonds use the unhybridized p orbitals. So whatever is left over is not hybridized. That's where you can get your p bonds. So if we looked at CO2, if we were to draw it, would look like this. We'd have our oxygens here. And then it says, what is the shape? And we know it's linear. And the bond angle is 180 degrees. So we're looking at the carbon dioxide molecule as a whole. So if we were to look back at that carbon dioxide molecule, what we would see is that there are 2 domains around the carbon, 2 electron domains. So you're going to take one s and one p. That's where your 2 electron domains are coming from. It gives a linear arrangement, which is what we saw, and it's going to leave 2 of the p orbitals not being used. And those are the ones that are going to be needed to form the pi bonds that we see in carbon dioxide. So here's the energy diagram for this one, your 2s, your 2p. This time you're going to leave 2 of the 2p orbitals on their own. So they're going to stay up there, they're not going to be hybridized. Here's the sps that are hybridized. Those are going to be your sigma bonds, the ones that go in between the carbons and the oxygens. Here's a picture again. You take your S with your 1p, it forms that mushroom shape, and you can see how they go together then to make the 180-degree bond angle. Now this picture shows a lot of information. So if we were to look here, this is CO2, and they reminded us of the Lewis structure right here. We need to remember that around the carbon was sp hybridization. And if we think back to the oxygen here, since there's 3 domains, 1, 2, 3, 3 electron domains was sp² hybridization. So looking at one of these oxygens, sp² has 3 electron domains, 3 orbitals, and that's what these greens are right here. This is an sp², this is an sp², and this is an sp². And that's true for the other greens over here. Around our carbon, we only have sp because there's 2 electron domains. So these yellow ones are your sp hybridized orbitals around the carbon. The blues that you see around the carbons and the oxygens, those are your unhybridized p orbitals. So if we look, carbon has 2, because this would be like px, px, and maybe py. So it has 2 p orbitals that are unhybridized. This top and this bottom is just 1 p orbital, because remember that they are dumbbell shaped. So this leftover p orbital right here is pi bonding with the unpaired or unhybridized p orbital on this oxygen. And then the second p orbital that's unhybridized on this carbon is pi bonding with the leftover pi bond, or is bonding with the leftover pi, is bonding with the leftover p orbital, the unhybridized p orbital on this oxygen. So you can see where the double bonds come from. Even though this looks like a triple bond, it really only signifies a double bond. So you have your sigma bond in the middle going between the 2 nuclei with the hybridized orbitals, and then your pi bonds are existing either in front and in back, or on the top and bottom. It depends. So you can see how that works within that structure. We can go outside of 4 electron domains if we were to draw this one. It would look something like this, and I'm not going to take the time, but you would have all those electron pairs around each chlorine. So it says, what is the shape of this? And this is going to be trigonal bipyramidal. And the bond angles would be 120 degrees and 90 degrees. So there are your 2 bond angles for that one. Then it says it's a combination of 1d, 1s, and 3p's. Because if we think back to what we just drew, around that phosphorus, there were 5 electron domains. So this is 1 and 3, but there's only 3 p orbitals. So now we have to go into the d's. So this is 1 plus 3 is 4, plus another is your 5th electron domain. So there's where you get the 5 in terms of hybridization. It gives you the trigonal bipyramidal arrangement, and we get 5 equivalent hybrid orbitals. So here's a picture of what you would see. And if you think of the chlorines had all those lone pairs around them that we didn't draw, but they still count as domains around the chlorine. So each of these chlorines is showing sp³ hybridization because they have 4 domains. So each of these are identical sp³s. And that would be true for each of these chlorines. And then around the phosphorus, each of these is sp³d. And those are your 5 identical sp³d hybridized orbitals. The next one we have is xenon tetrafluoride, which if I were to draw it, you're going to end up with, oh boy, I didn't do that very well. Oh well. You're going to end up with 2 lone pairs of electrons and then your 4 fluorines around it. And it says, what is the electron domain geometry? So I'm going to ignore that these are lone pairs. I'm just going to count up domains. It has 6 electron domains, so this is octahedral. And then the bond angles on this are just going to be 90 degrees. But if you looked at this, because if we took into account the lone pairs right there, it would make the shape a little bit different. It wouldn't be octahedral, but they're not asking for that. So there's that. And then because there were 6 electron domains, there's your 1 from your S, 3 from your P, that makes up 4, plus another 2 Ds, and that's how you get to your 6 that you need, and that gives you the octahedral arrangement. And then here's another picture for you showing that there's what our Lewis structure should have looked like had I put all the lone pairs on all the fluorines. And then they arranged them like that. And then if they wanted to show it using the hybridized orbitals, we have 6 identical hybridized orbitals here. Each of these are sp³d2 hybridized orbitals. And then you have your fluorines attached. Okay, draw the Lewis structure for HCN. So here's HCN. That's what it would look like. What is the hybridization of the carbon atom? So I look at the carbon atom and I see that there's 2 domains around the carbon atom. So there is going to be sp hybridization around the carbon. And then it says showing all bonds. We want to draw HCN showing all bonds between atoms and labeling each bond as sigma or pi. So if I were to redraw this, so we can do that, this is a sigma bond, and as well as one of the lines from the triple bond is also a sigma. So you form your sigma bonds first, and then if you have to build on with like a double and a triple, that's where you go beyond to the pi's. So these 2 right here would be my pi bonds. They're the ones that are above and below, in front and in back of the atoms. They do not fall in between the carbon and the nitrogen atom. And then we're not going to take the time to do this, and you'll have plenty of practice in class. So that's it. You really need to make sure that you can draw those Lewis structures well. That way you can get the correct hybridization on each of these molecules. And then you also need to know those geometries and bond angles from memory, because you're not going to get to use the table when you get to the test.